Here we'd like to introduce a class of series called the p-series. So these will be series of the form 1 over n to the p. So a question that we can try and answer now is, for what values of p does the series 1 over n to the p converge? Now in this case we can use the integral test, but we have to verify a couple things first. So before we do the integral test, let's think about the conditions that are required for the integral test. So here we'll let f of x equal 1 over x to the p, and we'll consider the case when p is positive first. Because in this case, it's clear that 1 over x to the p and 1 over x to the p will be a positive, continuous, and decreasing function on the interval 1 to infinity. So that's just checking the basic conditions that are required in order to use the integral test. Okay, so since we know 1 over x to the p is positive, continuous, and decreasing on the interval 1 to infinity, then we can use the integral test to determine if the series 1 over n to the p is convergent for positive p. Let's see what happens when we integrate now. In fact, you may recognize this integral, which we studied before in the section on improper integrals. And we know the answer to this already. We've showed that this is convergent when p is greater than 1 and divergent when p is less than or equal to 1. Therefore, by the integral test, the same holds true for the p-series 1 over n to the p. So the series 1 over n to the p is convergent when p is greater than 1 and divergent when p is less than or equal to 1. And actually in this case, let's be more specific, because here we were also assuming that p is greater than 0. So we're just actually only establishing it for the case when p is between 0 and 1. Or showing that it's divergent for when p is between 0 and 1. So now we should consider the case when p is less than or equal to 1. Sorry, when p is less than or equal to 0. So that case we can use a different test. So if p is less than or equal to 0, then what happens when we take the limit as n goes to infinity of 1 over n to the p? Well, in this case, as n goes to infinity, 1 over n to the p is going to have a negative exponent here. And in particular, you're going to get something here that's not equal to 0. So two things could happen, right? So if the limit as n goes to infinity of 1 over n to the p would be the same as n to the negative p, and now negative p would be a positive value. So this could either equal to infinity or it could equal to 1. So when will it equal to infinity? It'll equal to infinity if p is strictly less than 0, in other words, p is a negative value, when will it equal to 1? It'll equal to 1 if p is equal to 0. And so in either case, though, we see that this limit is not equal to 0. And that's the key that we need to show that it's divergent. Because remember, we have the divergence test, which says that if the limit as n goes to infinity of an is not equal to 0, then we know the series is divergent. And that's exactly what we've shown here, is that the limit as n goes to infinity of 1 over n to the p is not equal to 0. Therefore, the series 1 over n to the p is divergent for p less than or equal to 0. So in general, we see for a p series, right, a p series 1 over n to the p is convergent for p convergent for p greater than 1 and divergent for p less than or equal to 1. Okay, and so here is the p-series theorem. So now we've classified for every series of this form, 1 over n to the p, we can easily see whether it's convergent or divergent, right? And we have many examples of series that fall into this category. We saw this one before, right? The harmonic series. Notice that this is a p-series with p equals 1. So this is a divergent, right? Because here we have p equal to 1, and that's greater than, or yeah, it's greater than or equal to 1, right? So I'm sorry, it's less than or equal to 1, right? So it satisfies this condition, so therefore it's divergent. On the other hand, if I have 1 over n squared, this is convergent. Here we have p equal to 2, which is greater than 1. And we can look at any p-series, right? We can look at the power, whatever the power is, determines whether or not it's convergent or divergent. Here are just some other simple examples. So the series 1 over n cubed, here, what's the p? In this case, it's a p-series with p equal to 3, certainly bigger than 1. So this is convergent p-series. Versus here 1 over n to the 1/3 power, this is a divergent p-series. Right? Notice this is like the same as 1 over the cube root of n. So here p is 1/3, which is less than or equal to 1, so then it's a divergent p-series. What about the series ln of n over n? How would I show that this one is convergent or divergent? So notice that this is not a p-series, so I can't use the p-series test. But something that I notice about this that is convenient is that I can easily integrate ln of x over x. And since I recognize that this has an easy integral to evaluate, we can use the integral test. So the first thing I'll check, though, is if the function f of x equals ln of x over x is positive, continuous, and decreasing on the interval from 1 to infinity. Now the positive part here actually requires x to be greater than 1, because ln of x will be negative when x is not greater than when x is less than 1. So here it is positive, but only on the interval from 1 to infinity. Is it continuous on the interval from 1 to infinity? Yeah, well, we see there's only one point where it would be discontinuous, and that's at x equals 0. So as long as the interval doesn't contain x equals 0, here 1 to infinity doesn't, so it is continuous. And is it decreasing? Well, to check decreasing, let's do something that we did in the past. Let's take the derivative and check that it's decreasing. So a little bit of quotient rule here will give us the derivative. The derivative of ln x is 1 over x times x minus the derivative of x is 1 times ln x over x squared. So this simplifies to 1 minus ln x over x squared. And we see that this will be negative as long as ln x is greater than 1, which means that if ln of x is greater than 1, then x is greater than e. So it will be decreasing, but actually it starts decreasing after e. So maybe from 1 to infinity would actually not be decreasing the whole time, but only for x greater than e. So actually, in this case, it would be decreasing from 3 to infinity. But that's okay, as long as it's eventually going to be decreasing. So now that we see that it's satisfying those three conditions, we can apply the integral test to ln of x over x. So we want to evaluate the integral from 1 to infinity of ln x over x. And so I'll write this as the limit as t approaches infinity, integral from 1 to t. Now, what I'll notice is that this integral will be easy to do a simple substitution. If I let u equal to ln x, then du will be 1 over x. And that takes care of the 1 over x that we have in the integral. So this integral just becomes u du. I'm going to actually change my limits of integration. Instead of 1 to t, it's going to be ln of 1 to ln of t, since we're integrating there, or since we're substituting, so I also have to change those limits of integration. And now when I integrate it, it'll be 1/2 u squared. Ln of 1 is 0 to ln of t. So this will be the limit as t approaches infinity, 1/2 ln of t squared minus 0. And as t goes to infinity, of course, ln of t also goes to infinity. So since this integral is divergent, it implies that the series is also divergent. So the series in this case, ln over n, ln n over n, is also divergent. In this case by the integral test.